Hello, scholars. So today I'm going to teach you about the independent samples t-test and everything that goes with it using JASP. This includes interpretation of all of your results, so that could apply to any statistical software. All right, so I have my data file here, and today I want to know if there's a statistically significant difference between genders, male versus female, in performance. Here's my performance scores. So I'm going to first order my t-test. So I'm going to go to analyses if it wasn't up already, t-test, classical independent samples t-test. And an independent samples t-test tests for a difference in mean average scores between two groups. So this means that the groups are not related, such as one person cannot be in both groups. So we have independence of observations. We have one dependent variable measured at a continuous level, and that means it could be measured along a continuum. Okay. And we have one categorical variable with two groups. So you can see I've moved them from my testing over here. I want a studentized t-test, a student t-test. That's the parametric version, in case you're wondering. And my hypothesis is that the alternative hypothesis is that the groups are not equal. I am going to test for normality and homogeneity of variance using Levine's test. Okay. And we can go back and order more descriptives later, but I'm going to go ahead and order my descriptive statistics right here. Okay. Now, here's how I interpret the results. First, I want to know if my data is normally distributed. It is. If you remember, here's my test of normality. The null hypothesis for normality testing is that the data is normal. My alpha is set at 0.05. It always will be for social sciences. So P, if it's greater than 0.05, is not significant, and I fail to reject the null. If P is less than 0.05, I reject the null, and it means the data is not normal. My P equals 0.115. That is greater than 0.05. So I fail to reject the null. Hence, the assumption of normality is met. Okay, so if I go to write that out right here, it'll be W equals, and I'll get my statistic. And in my case, it was 0.970, comma P, that's the P value that helps us determine whether or not we reject the null hypothesis. My P equals 0.115. Okay, so my assumption of normality is met. Now, if P had been less than 0.05, the assumption would have been violated. Okay. All right, now the next thing I want to check is my Levine's test. Is there homogeneity of variance? And remember, I covered in a previous video about equal variances, but we want to know if the distance between the scores for men and for women on performance are approximately the same. The null hypothesis is that they are equal. If I have a p-value of less than 0.05, I reject the null. My p-value is 0.971. Thus, the assumption of homogeneity of variance is met. I fail to reject the null. My variances are equal. So in my case, my assumptions are met and I can proceed to the t-test. But let's say your assumptions were violated. We would want to go investigate why. So I might look for outliers. So to look for outliers, I've got to go back to descriptive statistics, descriptives analysis, descriptive statistics, and I've got to order a box plot to look. So I'm going to do the same thing. I'm going to split it on gender. I'm going to put performance in the variables. And then I am going to go to statistics. I'm going to select quartiles in case I have outliers, right? And now I'm going to go down to customizable plots down here. I'm going to select box plot element, and label outliers. Okay. And what I'll get is a box plot showing me if I have outliers. If my outliers are greater than 1.5 steps from the edge of the box, they're significant. And they could be affecting normality. I have 2 outliers for female. Case number 1, female performance, and case number 33, female performance, and no outliers in male. Here I have a different example for you all ready to go on how to determine if those outliers are significant. You can see I have these circled, and we're going to use the interquartile range, which is why I ordered that for you. See, we ordered it when we did our dot box plot. Here's the range. You need that number, and you'll need 25th and 75th percentiles. So for the lower threshold, it's 1.5 times the interquartile range, so it's 0.690. And it's the quartile 1, which is the 25th percentile, 3.188. So 3.188 minus 1035, because I've multiplied this already. Once I'm done, 2.153. Any scores that are below 2.153 are a significant outlier. Okay, and I do the same thing for the upper threshold. If it goes beyond a certain number, and I use the quartile 3, 75th percentile number, and I take the interquartile range, which we already said was 0.690 in this case. We multiply that times 1.5. I get 1035, 1.035, sorry, and we add them together. And any score that is above 4.912 in this case would be significant, greater than 1.5 steps from the edge of the box. Okay. So I would be able to take my interquartile range. Oh, let's add that. Sorry. Got to make sure that IQR is checked as well. And I can use the interquartile range. And here I have them for male or for female. Make sure you select the right group. And there's my 25th percentile for the lower end. And for female, we only need to calculate the lower end on mine because I only have either of those, but we already know mine is not significant. Now, when you have an outlier, you check to see if it's correct. You check to see if there's sampling errors, but we don't just remove them. But if they're causing normality to be violated or homogeneity to be violated, we might select a different test. So if we go back here, and now we look at our independent samples t-tests, because mine met all of the assumptions, okay? We can interpret our independent t-test, which is up here. It's this one, okay? Mine, again, the null hypothesis states that they're equal. They're the same. If they're not equal, it'll be significant. My p-value is 0.287. That is not significant. I failed to reject the null. Now, if I wanted to write this up in APA, let me show you how I would do it. Okay. The APA, I call it the number sentence. It's not really a number sentence. It's going to be T with your degrees of freedom, which is going to be your sample size minus 2. I had 64 in my sample, but degrees of freedom is listed right here. It's on the table, right? T 62 equals, and I give the T statistic first, minus 1.074, comma, P equals 0.287. I fail to reject the null hypothesis because P is greater than 0.05. Okay, refer to the hypothesis testing that I gave you. And this is a lowercase t. Okay, so that's how I write it in APA 7. Now let's say I found something and I had a significant difference. I'm going to go back to my t-test. I'm going to add an effect size. See that over here? Here's the effect size. And I'm going to use Cohen's d because Cohen's d is my favorite. And an effect size, that means how big of a difference is there? If there's a great big difference, it'll show up with the effect size. Well, here's Cohen's d, minus 0.269. Now there's something called Cohen's cutoffs, small, medium, and large. And we can find that here. There we go. A small effect size is 0.2. Mine was minus 0.2, and that doesn't matter. The positive or negative sign doesn't matter there. Medium is 0.5, and 0.8 or above is large. Okay, but I did not have a significance, so the effect size doesn't matter. But let's say I did have a significance. How would I write that? Now I'm going to add D equals 0.2, a small effect. Okay, so I have to identify that. It's a small effect. I'm going to use those Cohen's cutoffs. If I don't find a difference, sometimes I can do a post-hoc power test to see if my test was too weak to find something. Sometimes the test is too weak if the group sizes are really unequal, like I had 25 in this group and 75 in the other group. The ratio is 1 to 3. So if you're ever asked what the ratio is for the group sizes, they want to see 1 to 1. But maybe it's 1 to 2. When I'm getting into 1 to 3, they're terribly unequal. And then I might stop and resample the larger group to match the smaller group. Or maybe my sample size is just too small. I can check that out as well. I can order a post-hoc power test. I use G-Power. It's free. Some softwares automatically you can order the power of the test, but I'll just go there. I'll select t-tests, means, difference between two groups, and I want post-hoc power. I did a two-tailed test. My alpha was 0.5. My effect size was 0.2. My sample size was 64. So I had 32 in each group. Okay. And look, my power is 0.123. That's a really weak test. If you remember when I taught you about hypothesis testing with errors, I said social sciences uh, can use a power of 0.18. We usually use 0.95 because we set our chances of a type 1 error, the alpha, 0.05. 100% minus 0.05 is 0.95, right? So this is a really 0.1. That's a really weak test. So if I were reporting this, mine, I would say the sample size was too small. So if I were doing this in research, I would say I would say G power to conduct a post-hoc power test. G power was 0.12, a very weak test. Researcher recommends a larger sample size. Now, let's say I want to try a non-parametric test because my sample size was so small and everything was just so weak. My non-parametric test, because my assumptions were violated, if you had a violated assumptions, you could run a Welch test or a Mann-Whitney U. Mann-Whitney U is my favorite because it tests the medians instead of the means. But I can order that right now, right here. I can go back and it will update it. So here on the t-test, it shows up. And my p-value was 0.467. Still not significant. There's no difference. And the effect size was even smaller. So no difference. But I can always make the recommendation if normality was violated or homogeneity of variance was violated, I can go to the non-parametric test if resampling or sampling more is not an option. And for your dissertation, it won't be. Okay, so how we do it, we normality check, the null hypothesis says that it's normal. A homogeneity of variance, which means equal variances between scores, the null hypothesis is that they're equal. If these are violated, your assumption is violated. If your assumption is violated, go to a box plot and see if you have outliers causing the problem. significant outliers greater than 1.5 steps from the edge of the box. If your assumptions are not violated, proceed with the t-test. If your assumptions are violated, a t-test is robust to violations of normality. You could probably proceed anyway and argue that, or you could do the Mann-Whitney-U or the Welch t-test and run that instead. And I only order an effect size if I found something. Okay? If I didn't find anything, there's nothing to order. Okay, effect sizes are only for when I find a significance, because that answers the question, how big of a significance? And then we can talk about the mean differences in scores, right? We can order the mean for each of these. I might want that because look, I see the mean difference, but I don't see what the mean score is. Oh, here's the mean. Okay. Women had a performance of 30.78 and males had a performance of 34.2. But I can also order that in my descriptive statistics. Remember, I can go back and I can add mean, median, and mode, which I might want to do if I run a different test. Okay. I can add skewness and kurtosis in a normality test right there, if you remember, right? So the mean for women, it's updating. Okay. It says the same thing the other one does. All right. That's all I have for you on the independent t-test. Please reach out to me if you have any questions.